What's the time now? 7:30. 13 in 2 minutes.
It's quite top standard. The classical mechanics theory problem, which is solving the other is zero.
And this summer I did an internship. So yeah, in this talk I'm just kind of going to go over and share it with you. So yeah, I'll introduce that with introduction. And then, so in this talk, I thought of a set an objective for what our goal is, what we're trying to do, and then take you step by step to how we go about solving a problem in physics. So first we'll do a reference frame transformation. Then we'll plot effective potential surfaces. Then we will compare integration algorithms and decide which one to use and why. And then finally we'll look at popular satellite. Yeah, basically applications of this. So orbital dynamics is Lagrange point. But do we know what it means? Right, okay. So why orbital dynamics? What is the difference between what is dynamics? Be louder? Oh, sure, yeah, okay. Dynamics as compared to statics is the study of moving objects, and they both come under the field of study in physics called mechanics. Yeah, classical mechanics. Dynamics sort of gets divided into kinetics and dynamics. Kinetics deals with the forces acting on the body at its start and end point. Kinematics deals with the trajectory. Here, because we want both the forces and the initial final conditions as well as the trajectory. What will do is orbital dynamics. Now, what is an orbit? Can anything be an orbit? Is this an orbit? Is a circle an orbit? Yes, no. Is an ellipse an orbit?
Yes.
Is a spiral an orbit? Is a parabola an orbit? Is a hyperbola an orbit? Is a sine wave an orbit? Why not? If it's not necessary that only closed shapes are orbit, then why is a sine wave not an orbit? Conic sections. So is the spiral not an orbit? It's only conic section. But spiral is not a conic section. Yeah. Orbit is very simply defined as a curved trajectory of an object bound by a center. An object that is moving under the edge of okay, so if we say orbit, Kepler, just using observational data, he just sat and looked at this type of medium and came up with three revolutionary works that changed physics. So yeah, Kepler, however, only referred to closed orbits and only of those of planets around the sun. So Kepler claimed that all orbits are elliptical and the sun is one of the foci of the ellipse. He also said that the area velocity is constant anywhere in the orbit. Air velocity basically means that if an object is moving around the sun, then the area that it sweeps in a given time is fixed. So yeah, that's area velocity constant. And the orbital time period is proportional to its size. Or if I have to be more specific, T square is proportional to A cube, where A is the semi-major axis of these will capture three laws, and this is where we start. When we talk about orbits, we start from here. Now, Lagrange points. What are Lagrange? Like he mentioned in the starting of the talk and like he introduced, there you can say that there is kind of solutions of the three body problem, a specific case of the three body problem, to be exact. It's called the circular plane restricted three body. So we're only looking at those objects moving in a circle and it's plane restricted, meaning not in 3D, only in 2D. And yeah, and it's restricted three body problem in that we don't actually consider three masses whose gravitational forces are acting on each other. We consider two masses whose gravitational forces are acting, and the third object who is influenced by these two is not related. That's what the circuit. Now, how do we set up this problem? I'm going to say, and there is another one. And these two are in a mutual orbit. They're mutually orbiting each other, they're gravitationally affecting each other. And we're going to say they're moving in a circle. And so now, in the presence of these two and their gravitational field, if you bring in a third test mass that does not exert its own gravitational field but has a mass hypothetically somehow that gets affected by these. This test mass in this gravitational field, combined gravitational field, so two masses, these two are exerting a gravitational field, and now in the area of their combined gravitational field, we have a third test mass. This test mass basically Lagrange points are those points in this field where this test mass will lie in equilibrium. So basically, where all the net forces cancel each other. And I'm sure that everybody would have solved this problem. This has a gravitational force acting this way. This has a gravitational force acting this way. There must be some point somewhere. But here is the first Lagrange point. Now this has a gravity. Now another factor comes in. If these two are moving around each other and then we transform to different planes, then we get other forces like centrifugal force. Now, when you have centrifugal force always acts outward from the center of the plane. We look at Lagrange transformations exactly how they work, but the centrifugal force acts outward. Now, here there will be a point where this gravitational force acts this way. This gravitational force also acts this way, which is smaller in magnitude because of distance. And then the centrifugal force acting up. So there must be a point somewhere here where we get. And similarly, a point where here where we get. L2 and L3. Now L4 and L5 are interesting. L4 is here, L5 is here. Thus that they form an equilateral triangle with this length, and this length are equal. Now, I have to get into the details of how exactly we see this, but we can kind of guess now. It's acting this way, it's acting this way, and so their horizontal components here will cancel. And they will get a net vertical component this way, centrifugal force acts outward, straight. So we get 2 points here and here, L4 and L5. Yeah, and so now why are these equilibrium points equal? That also we will look at the end. Okay, so now what is our goal? We want to plot the trajectory of the third test body in the presence of a gravitationally bound two-body system. So gravitationally bound two-body system we have, third is the test mass. Now, if you put this test mass in random points around these two, or in the presence of these two, how will they move? That is the question that Lokesh is solving. Now, First, we're going to transform into a appropriate frame of reference. This is just for convenience of solving the problem. Then we have to set initial term. Then we find the net forces acting on this third test mass. Or we can find the effective potential. We know that our forces are derived from a potential. We call conservative forces are derived from a potential. So if we find the effective potential, that also works. And then finally we need to integrate to find the potential. So usually problems in physics, we start with the forces. So we know what all forces are acting on an object. And if we know the force and we know the mass, that means we know the acceleration. And so we go from the acceleration to the position function, which means we have to integrate twice. So how do we do that? So you might find a heard that the three body problem is like unsolvable, right? So why is it unsolvable? Because the three body problem basically gives us a differential equation that is of the fifth order, which means we can't solve it. Like we don't have the mathematical tools to integrate such an equation and reach the. So then what do we do? Okay, before we get into that, let's look at rotating system reference and how they work. Centrifugal force. Say you're in a rotating frame and holding a ball. As long as you're holding the ball will move where it is in that same particular. But then imagine you drop the ball. Now from our point of view, the ball will move in a straight line because inertia. There is nothing to make it rotate anymore. And so it will continue to move in a straight line. And it will reach the end of your frame, like the bottom of the. But now from the rotating who's holding the ball, it appears as though the ball kind of straight fell down. Even though there is no force acting. This is centrifugal. It's a pseudo force because the rotating frame is non-inertial in nature. And yeah, now there's also another pseudo force that is called the Coriolis force. Now the Coriolis force is basically, so these concentric circles are the velocities. On the axis, points in the circle will move with different velocities. Outside one will move faster, inside one will move slower. This first, we can throw the ball upward. Because it was part of this concentric circle, it will have a large horizontal component of the velocity. But then as it moves up, because those parts of the frame are moving at a slower pace, it will seem as though this ball is moving faster ahead. So it will seem as though there is sort of a perpendicular force in this frame when there is not. That is simply because its velocity is that of its original point. The horizontal component of velocity is that, so it will. So as though it moves faster in that direction. So there is some horizontal push forward. Okay, yeah. So that's the Coriolis force. Any doubt? Rotation frame here. Okay. So basically we have two pseudo forces that are acting in the frame. So now I will not go too much into the math because first year. But yeah. So you have no rotation matrices. Rotation matrices by now? No. Okay, that's fine. This is not numerical. This is our normal range. Now, okay, if I rotate the entire frame of reference into here, like this by some angle theta, whatever my x and y coordinates were, it will become x prime and y prime coordinates. And by doing this rotation, every point that is on this original xy plane will now become a different point on the second. We usually represent this using the rotation matrix in x dash, y dash. Cos theta, sin theta, cos theta, cos theta. This is basically how frames of reference rotate. Now if we do this, we get x dash and y dash. We differentiate x dash and y dash to get dx dash and dy dash. Differentiate this again to get ax dash and dy dash. This is basically how we rotate. Now if you solve this matrix and you differentiate it twice, which takes normal forces were acting on your plane. So here if I have a body and there was some force F acting, whatever that force F is will also act on this. Plus, you will get the centrifugal force component and the Coriolis force. Fair enough? Yeah. So, yeah, centrifugal force is this you guys know, omega square. And Coriolis force is 2 omega. And the vector product is omega and minus 2 omega cross B. But yeah, that's the magnitude. Okay. So now that we are in a rotational frame of reference, we need to set the initial condition. The problem in physics has 4 initial conditions. X, Y, Z, X. I mean, it was okay in 3 then 6. But basically, we need both the position and the initial velocity. Right? These are 2 initial conditions we have to set. Now, name of the topic orbital dynamics near the Lagrange. We have to set where the initial position is. Where is the Lagrange point? So, we set initial position near there. But we know that possible is unsolvable. Right? Differential equations that you can't solve. Then what we do? We use Taylor expansion. So yeah, basically N1, 2, N3, N4, N1, N2, N3. We can solve with Taylor expansion. Alpha and alpha, even if you use Taylor transformation, you can't solve. But Lagrange, he claimed that there is an alpha equilateral transformation. Claimed he was that is where they are, that will now prove it. And so then you can use a geometric proof to state why alpha and alpha will be true. If you start from the fact that they will be at equilibrium, so quite guess, and then he turned out to be right. But yeah, so there is a geometrical proof, so we know for sure where L4 and L5 are. Now for any particular system, if you say this is M1, with M2, and you call capital F, mu is equal to M1 by M2, where M1 is less than M2. Right. Now, based on each system has a unique mu. Like if we're looking at sun Earth system, this is the sun, this is Earth rotating around the sun, revolving around the sun. Then we will get a unique mu. For the sun Earth system, that 1 by 30. For the Earth moon system, that 1 by 81. Now, these are such small numbers. 1 by 33 are small numbers. We use approximation and we can see. So for the sun Earth system, okay, so this new rotational frame, I forgot to tell you that side, my friend. This new rotational frame, it has its origin at the center of mass of these two masses. So we have these two masses and we set up this new reference frame. Thus that its origin is at the center of mass. The x-axis of the coordinate system is the line joining the center of these two masses. Y-axis is this coordinate. Z-axis is this coordinate. Okay. So for the sun of system, because sun is so much heavier than Earth, center of mass is in the sun only. So the origin will be in the sun. And so we will get L1. L1 is in between these two, and the mass is so skewed to this side that the gravitational force of this is so much higher. L1 will also be in the sun. Or rather, very close to the sun. Not in the sun. Very close to it. Because in the sun, L1 very close. L2 is how much ever distance is there from sun to Earth. This is distance from sun to Earth. That same distance away from the Earth is L2. So however far this is, the same one on the side, let L2. Now, L3 for the sun systems, whatever is this distance, again on this side, L3. I put it as equal, right? Good. Okay. Now that we have sort of approximate idea where these points are, we will move on to the next step. Okay, effective potential. So now we know what the forces are. We have changes in rotation. We know what the forces acting on this, which means that we can come up with a potential. And so, yeah. Now, say these are two masses. This is the potential. So, okay, what are the forces we have acting now? Gravitational force, because the force that was acting on our original plane. Plus, now by rotating, it has centrifugal and Coriolis. Coriolis force, however, is non-conservative in nature and cannot be derived from a potential. So, in the potential, we will only have a gravitational at a centrifugal. Now, yeah, you can kind of see from this graph, if this is where the two masses must lie, because here there is an extremely large negative potential. This is like an infinite potential where right? This is where the two masses lie. And so, like very close to the masses, gravity is very clearly the strong. Another element points here is where centrifugal force sort of starts dominating over gravity, and then the potential becomes positive. Right, and then after that, once again, gravity takes over because when R becomes very high, 1 by R square, and so again the potential. Now, this is for two masses that are equal. So, you can see both the circles are sort of equal radius. Lagrange points in this okay, so Lagrange points are where they are in equilibrium. That means force is zero. If force is zero, then the first differential of potential is zero. But force is the gradient of potential. Force is the first differential of potential. So where are points in this graph where the slope is zero? First differential is the slope of the graph. So if the slope is zero, there are two very clear points of maxima here and here. Right? These points are maxima, so there is a zero slope tangent. These are L4 and L5. Now the other three are a little bit interesting. So here there is a point. Here also very clearly the slope is zero because there is a point. You know, see where the slope is zero, see where I am talking about. Here in between, and here. These are called saddle points. So in 2D we only have maximization. But in 3D, we have a third type of critical point called a saddle point. So if you look at your knuckle, in between two knuckles, there is like a valley. If you look at it face down, that is the minimum very clearly. But if you look at that same point, kind of turning your fist around 90 degrees, that's like the maximum. There's a slope here this way, and this is the maximum value. But if you look at it like this, the graph is this way, this is the minimum there. The saddle points are basically those points. But whatever it may be, its differential is zero. Saddle points are not as stable as maxima. So L1, L2, L3 are not stable equilibrium. They are equilibrium points, but they are not stable. And we will see where that comes later. Now this is if two masses are equal. If the two masses are say not equal, and we have a skew like this, then what happens? In the equal plots, you will see that wherever I'm putting my mouse, lines it was drawn with correct. These lines are basically called level curves, which is in the z-axis if you cut off it like that shape it takes. But this particular z value, if I cut it off, this is the cross-section shape of the plot. This is a very interesting shape. There are a lot of fun interesting shapes that come up in this level curve that we will also see. Yeah, that was the first one is our equal masses. Here, one mass is 8 times heavier. This mass is 8 times heavier than this one. And so this is how it skews. If we were looking at something like the Earth-Moon system, which is Earth is 81 times heavier than the Moon approximately. This is what you see. So you see that the Moon like barely a dent on the surface. And we can also look at similar shapes in the same. But the point is, this is the surface. The effect of the moon is very little bit, but at certain values of Z, it is considerable. Like if the moon was not there, this should be a circular orbit. Which here is a circular orbit, here is a circular orbit, so that is fine. But in some places, the effect of the moon is a lot clearer. And the moon is only 1 by 81 times the Earth 1. In the Earth sun system, the Earth is like 1 by 33,000 times the Earth. Anyway. Yeah, so in the Earth sun system, the effect will be less. Okay, so now that we have all of this, let's get into integration algorithm. We're going to solve this algorithm. Okay. I have the elements I want to find. Finally, I want to explore. In between, I need to find velocity to do that. Right? Now, my answer is in an unsolvable differential equation. Then what we do is cases where we don't have the math tools to solve it is we rely on computers. Computers solve it. So what the computer will do is it will take every point, we give it an initial point, and it will take a very small amount of time delta t, and it will see the acceleration, the force acting on this, and from that force, it will, and it has initial velocity v. With this initial velocity, with this delta time, it will move a very small sector. And then because of the force acting on that, and with the new velocity given at this point from this initial velocity. Yeah. So, yeah, initial point, this is our initial point, right? You're going to give it an initial value and the V value. And it has some initial force there. Now, we're going to say that for a very small factor, say this time interval is delta t, which is very small. After this time interval t, the computer will just plot if this right? So if we want to find the velocity, this is initial or this is the inertia. Now the velocity at the second point, so this point is 2, V2 will be equal to V1 plus whatever acceleration that we give into this small time. That is how much the velocity will change from here to here. Now R2 is equal to R1 plus V1 delta V. V1 is some V, but we're going to say V1 because at first we only have V1 in. Then when we get V2 information, use V2 to calculate V3 at this point again after some small delta t. The computer it wants to integrate this acceleration to get a whole function that does the entire trajectory of this point. So we cannot get this function out of k from a. What we can do is we can take very small delta and see from here where will this object go next, where will this object go next. And do that, make a computer do that like 1,000 times, 10,000 times, as many times as you want to. And then we will get the trajectory of the object. This is how we analytically solve problems, numerically solve problems that are analytically answered. Okay, this is what I just explained to you. The most basic integration algorithm. I'm using this to find this point, and then using the velocity here to find velocity here. Then I'm using velocity here to find velocity here. We have some kind of approximation. So basically, approximation of differentiation, where C is an infinitesimal element. Now, when we do approximations like this, we need to make sure that the energy is conserved. So we write code for this integration algorithm. And then we write the energy function and the angular momentum. plot that over time and see is the energy remaining constant in the angular momentum. So now we have in this also explained to you that was Euler's integration rule. It's first order, most basic. Kinetic energy sort of decreases over time, potential energy sort of, and total energy sort of increases over time. Right? It's okay. It's not great, but it's okay. Angular momentum, still. Look at the angle. Over time, it's just increases. This function does not follow physics. We're going to look at a pattern. Then what we do is leapfrog. Now leapfrog is another integration. That is second order. Most intuitive. Okay. The problem here is at this point, because the force is acting continuously over here, the velocity is changing throughout this. So the velocity, the position here will not really be this velocity times delta t. Because the velocity from here to here is changed, here to here is changed. What is the easiest fix for this problem? I will find the velocity at the midpoint. I will find V half. And I will say V half is equal to V1 over V into delta t by t. Most basic fix, give the Thomas model. There are a lot of other integration algorithms that can like work even better. But for our problem, our energy is much better conserved as compared to frequency. This energy here, conservation is a lot better than this. Kinetic energy, more uniform graph, potential energy, more uniform graph, total energy, very easiest. Angular momentum is also conserved a lot better. There is a small fluctuation, but the fluctuation is located at 10 raised to minus 12, which is forgivable. So we're like, okay, good enough for us. There are other problems that you can't really solve using leapfrog because it's only second order. You might have to go to third order, better order than this. But for our, this is good enough. Okay. So yeah, now we have the cool stuff. Say by static initial conditions near L4. Say by static initial conditions near L4. We start this object from somewhere near here and we give it no initial velocity, zero initial velocity. If you keep it on L4 with zero initial velocity, what will happen? I am putting a test mass exactly at L4 and not giving it any initial velocity. What should happen? It will stay over there. But there's no force. No, it does. Away from this point. But if we keep it very close to L4 and give it no initial velocity, then it will orbit around L4 in this one little shape. This is called a tadpole orbit, which is a very weird shape. Look at it. But the point is, there are actual asteroids that follow this orbit. There are satellites that satellites are actually, yeah, we come to satellites. But there are asteroids that actually orbit around like this. Horseshoe orbit, we also start from near L4, but we give it some initial velocity. And so then what happens? It basically starts from here, goes all the way like that close to this point, and then turns around and goes around all the way around like that, comes back to here, turns around again, goes around and comes back here. This is a horseshoe orbit because it's shaped like a horseshoe. And if you put an object here and give it some small velocity, this is the particle column. If you put an object here and give it a lesser velocity, then it will just do that. Actual asteroids that follow this orbit, you guys might have seen it aligned with NAC, Janus and Epicenius. So why that happens? These are the orbits that end, which is why they do that fun little dance that you guys would have seen in other languages than NAC. Aditya, what do we know about Aditya? Yeah, so Aditya L1 sits at L1. And why would we want to put satellite? What is the purpose?
Because so they stay at the point and they react to information. We don't need to go in extra.
Yeah, exactly.
It is stable.
Exactly.
And it will be always between both Earth and the Sun, so we can make connections very easy.
Yeah, okay. L1 is very close to the sun. So that is one thing why it's an L1. And like we said, we don't have to use fuel. It's a stable point. If it's there, no force is activated. It will just sit there. Carefully just orbit the sun. No extra force taken. But we saw that L1 and L2 were unstable equilibrium points, which means that only a hypothetical mass that does not induce a gravitational field, that is exactly a point, if it is kept there, it will be safe. Satellites are big, they have zero mass. Compared to the sun, sure, it's nothing. But also they're big, they have massive size. And so, the code that I wrote to plot that code is possible. Use that code to plot other than see a very fun, unstable secret that we should if sun is here, if you keep it at L1, it will still I'll get one to in American. If you just keep it there. Okay, so all of the plots that I showed you that I'm also meaning that this line between this from center of mass, the whole thing is rotating. In that rotational frame of reference, if I say that this is basically spiraling out of orbit, that means that in a normal, non-rotating frame of reference, it kind of will shoot up. However, this was still kept as that alone because it will shoot up a little bit and then it is a little bit you to adjust it back. And so there is some fuel that goes into it, there is some adjustment correction that happens. But near L1, a lot less fuel is required. The mass of the sun is a lot more than the mass of the Earth. Yeah, definitely. Yeah. Without it, it's a lot closer to Earth. But it is closer to the sun than Earth is, and it is So it will be closer to the Earth than it is to the sun. But L1 is closer to the sun than Earth is, and any points, and it's the basically Lagrange point that is true. It is my bad, I made a mistake. Because the sun is so much heavier than the Earth, its gravitational pull will be a lot closer to it. Further away from it, near the Earth, its gravitational pull will be less, Earth's gravitational pull will be more. Leaning more towards the Earth rather than my bad. But point is that it's still a position of equilibrium. Even though it's unstable, it's a position of equilibrium. And if you keep something there, hypothetically, it just sits there and orbits around the sun along with Earth. So it kind of moves the same moves at the same speed or moves in the same basically angular velocity around the sun. It doesn't do that, it shifts a little bit, but we correct its orbit every now and then. Same thing with JWST. And JWST sits at L2 and it sits facing away from the sun because it kind of wants to avoid all of the light pollution from the sun so that it can also far away. So it sits at L2 again, same reason, same angular velocity as the Earth. Sun. Also, it was put at L2 because stable point, because equilibrium point, very stable point. So they also use it as a correction for JWST. Now Chandra, but you guys have also seen this image of Chandra and orbit like I did earlier. It basically orbited around the Earth and then got pulled into orbit of the Moon. That point of transition is a direction. Where Earth then point of like this, initial escape velocity, orbit the Earth, orbit the Earth, orbit the Earth. And then it gets swung into this moon orbit and then does very beautiful soft landing on the moon that first of all, yeah, but we will see that. Anyways, this point basically, where it swings out of the Earth's orbit and into the moon orbit, that's the Lagrange point. So, yeah, Lagrange points are everywhere. You have to look for that, you've got to start seeing them in more things. That's it, that's my talk. Thank you. Sorry about L1 and yeah. No, I mean, it depends on how good you want to approximate. You can take it into, you can take centrifugal force into account and approximate, but you can do it like that. Again, depends on if it's Earth Sun system, the mass is so skewed, nothing really matters. 1/53,000. L1 and 2 L3 are approximation. Yeah. Rotating like one. Yeah. L1 will be near the. Yeah. There is a centrifugal. If we don't do centrifugal force, then it's a point. Another way to calculate the difference if you don't want to use a function is when you have a potential surface, you can use something like Newton-Raphson algorithm to find the critical. So that's just but yeah. So basically, when we have 3D surfaces like this, there are algorithms to find their critical point. Yeah.
For here, your second derivative is also
Yeah. Yeah. So there are Newton-Raphson modifications here. So basically, now we just write this as a function, and we can use math to find points where the slope is zero. The way that for normal 2D function we find first derivative, then set x equal second derivative is equal to zero. You can do that in 3D also, and then we can find more exactly where the critical points. That's a better way of locating the exact points if you don't want to do approximation. Yeah. Say, you find Lagrange points in the rotation. Right. So, in the standard system case, you're saying that the distance between the center of mass and the L1 point would be negative. No, the L1 will be near Earth. Center of mass will be near the sun. So, I mean, if you have to calculate the L1 point. Yeah. Wait. Yeah. Centrifugal, yes. Yeah. If you don't take a centrifugal force into account, then the center of mass is the sun, and the center of mass is the sun, and then it will be Earth. Then yeah. Right. The solution exists. I think it's Integrable. We don't. I don't know. Yeah. Yeah, as far as I know, it's I don't even know why. What is this? So there's no third time now? Okay.
Not the VM.
Right.
It's
Yeah. Yeah, yeah, yeah. 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 So, yeah. Yeah.
what is the shape of those things? Anytime over the bench point.
Also circle.
Also be circle.
Also the circle. So, in the rotation plane, that point. Rotated back, it's the circle. Yeah, rotating. Anytime. The sun is Earth's Lagrange point. Earth is rotating around like this, this Lagrange point rotating around this one. Earth goes around this way. Okay. Yeah, circle is the circular plane restricted field. Circular plane restricted. So the third mass has mass to experience the gravitational field but does not dictate the direction. Yeah, exactly. Hypothetical. Yeah, that's the first
Class.